This is Bob Capetta, Professor of Mathematics at College of DuPage in Glen Ellen, Illinois. And this lesson is on the Mathematics for Health Sciences correlation coefficient. Now, a correlation coefficient is a number that reflects the relationship between two variables. So think about a set of x values, think about a set of y values, think about a graph of those points, and what we can say about those points. Now, the correlation coefficient is a measure of the degree to which changes of one variable predict the changes in the other variable. In the case that we have positive correlated variables, what that means is changes in the x variables correspond to the same sorts of changes in the y. That is, if x increases, y increases too. That will give us a positive correlation. If x increases but y decreases, that will give us a negative correlation. And we can think about that in terms of the slope of the line of interest. Now, the correlation coefficient is always a number between positive 1 and negative 1. Very, very rarely you may see a coefficient of positive 1. That is a perfect positive correlation. As x increases, y increases in a perfect linear fashion. And what that would tell us is if we would know the x value, we would be able to perfectly predict the y value. Perfect correlation. Now, the fact that it's positive, that tells us the slope of the line is positive. Change in y over change in x is positive. Perfect straight line, positive slope will give us a correlation coefficient of positive 1. A correlation of negative 1, also a perfect correlation. As x changes, so does y, but you'll notice it changes in the other direction. As x increases, y decreases. All of these values lie on that straight line, though, so that enables us to make perfect predictions. If we know the x value, we would be able to perfectly predict the y value. In reality, this rarely happens. If you had, for example, the relationship between degrees Celsius and the degrees Fahrenheit, indeed, that is a perfect linear relationship. That would have a correlation of positive 1. But in the real world, the correlations look more like this. So if we have a set of x and y data, we could have these numbers that are bunched fairly tightly along a line with positive slope. It's going to have positive correlation because the slope is positive, but it's not 1. The points do not all lie on a perfect straight line, but they are tightly bunched. You'll notice in the second example we can see a linear trend, but they're more spread out. So this correlation is smaller than the first one. So we're saying the first correlation is about 0.8, but the second correlation is about 0.3. But in either case, we certainly could make a reasonable prediction of the y value if we knew the x value. But in this third case, we're saying there's no correlation at all. It's just a cloud of points. Knowing the x value is not going to enable you to make any kind of prediction for the y value. When you see a cloud of numbers like that, that is indicative of a zero correlation. Now with these last two, notice that as x increases, y decreases. The slopes of these lines are negative. In the first case, the points are not tightly bunched, so the correlation is closer to 0, negative 0.3. In the second case, the points are tightly bunched along a line with a negative slope. So indeed it has negative correlation, but that negative correlation is going to be closer to negative 1. Which in this case is going to be negative 0.8. Now, zero correlation tells us indeed there is no relationship. So this cloud case is like the example we saw on the last slide. But this other case is an important one. The correlation coefficient that we are studying is a linear correlation. Even though these points lie in a perfect parabola, there is no line that would describe their behavior. So if you see some sort of a curvilinear shape other than a line, you're not going to get a correlation of any value. So if the points lie on a curve other than a straight line, you would expect a correlation of around 0. Correlations indicate the strength of the relationship. We have another visual of these things. Strong positive correlation, slope is positive, tightly bunched. Relatively high correlation. Here is a weaker one. The points are not as tightly bunched on the line. Negative correlation, strongly bunched along a line with a negative slope. Strong negative correlation. Here's one that's not as tightly bunched. relatively weak. And here it's in between. They're calling that a moderate negative correlation. And then if we take a look at the last slide here, it tells us there's no correlation. If the points are in a cloud, no discernible pattern, we would say there's no correlation, or a correlation of about 0. So just to kind of give us an idea about what these numbers mean, we're going to say if R is 0.7 or higher, we have a very strong positive relationship, a strong positive correlation. Similarly, if it's negative 0.7 or higher, but frankly it should be or lower, right? Negative 0.7 to negative 1, we have a very strong negative correlation. Strong positive correlation between 0.4 and 0.69, strong negative from negative 0.4 to negative 0.69. Moderate from 0.30 to 0.39, negative 0.30 to negative 0.39, etc. So you can see that whether it's positive or negative, the sign doesn't matter as much in terms of the strength of the relationship. Correlations close to 1 or negative 1 are strong correlations. Close to 0 are negligible correlations, not much relationship. Now what we want to do is we want to determine how to compute the correlation coefficient using Excel. So I'm going to pull up an Excel document. We're going to look at some numbers and see what the correlation coefficient is. So I have some old test scores for a total of 60 people. And we're interested in the value of the correlation. Now the correlation can be seen in a sense by looking at a scatter plot. So I'd like to do that. I'd like to select all of this data and construct a scatter plot. So all the data is selected. I'm going to choose the scatter plot under the Charts button on Excel. Mark the scatter plot, and I will move that so we can see it. And you'll recognize that there is indeed some sort of a linear relationship. As the X values go up, that's the score on test 1. The Y values go up, the score on test 2. There are some outliers. I mean, this person did better on test 1 than test 2. There was some declining performance, and there's some other people who did better on test 2 than predicted. But frankly, we can see that there is some sort of a relationship. We want to identify the strength of that relationship by looking at the correlation coefficient. So we'll go ahead and we'll do the command on Excel, and we'll see how that works. The command for correlation coefficient is equals correl, C-O-R-R-E-L. We have to highlight the two columns. So I'm going to do that. I'm going to highlight the first column, comma, highlight the second column of data. So we'll see how that goes. So I've got the first column highlighted, hit comma. I'm going to go back to the top and I'm going to highlight the second column. The second column is highlighted. So you notice my command here is correl A2 to A60, comma B2 to B60. We put in a parentheses here, and we see what we get. We get a correlation of 0.685. So, not quite 0.7, but fairly strong. There certainly is a relationship there between the variables. The letter that we use for correlation coefficient is R. So I think I'll go ahead and say R equals that value. So we have a correlation of 0.685. We saw our graph. We saw a relatively strong, or you want to call it moderate, linear relationship. So that supports the understanding we have of the correlation coefficient. Now there is a nice web page that will also do the correlation coefficient for you, so let me show you that now. So the URL is on the top of the page here, www.socsci-statistics.com/tests/Pearsons/default2.aspx. And you'll notice it says the Pearson correlation coefficient calculator, and there's the answer to the question that we just did on Excel. It says the value of R, they're choosing to use capital R here, is 0.6851. Now, the way that you do this is you take your X and Y values and plug them in. So we had those values from Excel, so I've placed those in already. And you'll notice after we do the calculator, it'll give us the scatter plot. So this is the same scatter plot that we had seen on Excel. And if you're interested, you can see the way all of this is computed. This first column is the z-scores for the x, almost, x minus the mean, y minus the mean, x minus mean squared, y minus mean squared, and the product of those two. So we can get some of that information from there, but don't concern yourself with that. Here's the rules if you'd like to look at it, but most importantly it tells us here that R equals 0.6851. And then it tells us what that means. It says the value of R is 0.6851. This is a moderate positive correlation, which means there is a tendency for high X variable scores to go with high Y variable scores. And then R squared in statistics is an important notion. That tells us how much of the variation in Y can be explained by the variation in X. What I want you to be able to do is I want you to be able to look at the graphs, maybe make an estimate of what you think the correlation would be, as well as use technology to compute the correlation. And that will end this lesson.